One more do it.
You're live, by the way.
So is it?
Yeah, it's on YouTube.
Like how many people are Hello, hello, hello. It is finally 1, so I think we will start our event. Can you guys hear me fine? All good? Can you hear me? Yeah? Right. So, welcome to the second seminar of the 1231, 1241 revision seminar. This part is going to be covering algebra. So, it's going to be like vector spaces, linear transformations, eigenvectors, eigenvalues, and then statistics. So I'm Ronald, and the person who's going to be presenting eigenvectors, eigenvalues, and statistics, that's going to be Lachlan Tobin. Say hi, hello.
Hello.
Okay, so I'm going to be doing vector spaces and linear transformations, and yeah, let's just get started. So let's start with vector spaces, and the first topic of vector spaces is subspaces. So the main thing we need to know is something called Subspace Theorem, which essentially says if we have a subset S, which is in a vector space V, and it's over the field F, it would be a subspace if it follows 3 rules. The first rule is that it contains the 0 vector of V. The second is that it's closed under vector addition, and the third is that it's closed under scalar multiplication. So closure under vector addition, it basically means if you take 2 vectors from the set S and then you add it together, the resultant vector would also be an S. And if you take a scalar and a vector from the set S, you multiply that scalar to the vector, that resultant vector should also be in S. So any scalar multiples of a vector in S should also be in S. So let's suppose that S is referring to the set of all vectors. So the way we read this is if there are curly braces, it means that it's a set, and it takes in all elements in the form of R3. So real numbered vectors to the third dimension, and this colon means such that this condition is true. So every single vector which has this condition to be true is inside this set. So either prove that S is a subspace of R3 or explain why it isn't. Okay, so So the first thing that we want to test is the first rule. We know that the vector space 0 is in S, so R3 has the vectors 0 vector 0, 0, 0, and since 0 satisfies the condition with 0 plus 0 being greater than or equal to 0, we know that it's in there. So now, to test vector addition, essentially what you do is you define 2 generic vectors, let's call them U and V, and they're in S. Since they're in S, you would say that their condition is true. So in this case, the condition for U is this, and the condition for V is this. And we can also consider what the resultant vector would be. So we can add these 2 equations together that we have from our conditions that we've assumed, and we get this, which is actually the condition for the resultant vector. So we've proved that the resultant vector would also be an S, and hence it's closed under vector addition. So the only 1 out of the 3 things have to be proven false for a set not to be a subspace. So in an exam, we would only do 1 of the 3 rules, and just prove it wrong to see that it's not a subspace. So in this case, is S closed under scalar multiplication? The answer is no. So what we can do is, to prove something wrong, we consider an example where it breaks. So what we can do is we can consider this vector right here. We know it's in the set because the condition works for it. And then we can also take a scalar. So generally, if it doesn't work, a scalar that it won't work for would be like -1 or a negative scalar, and then you just multiply it, right? So if we multiply it, we get -1, -1, -1, and we know that it doesn't work because the condition does not hold true for this vector. And hence, we can say that S is not a subspace as it's not closed under scalar multiplication. So let's move on to the next question. And this is the same thing. It just says all vectors in R3 such that this condition is true. We need to prove that it's closed under scalar multiplication. So what we do is, like the last one, we have a generic vector, but this time we want to find out whether when we multiply a scalar by a vector, it holds true. So we also have a generic scalar that we do. And then we consider what the resultant vector would be. And then we also draw conclusions about the vector we've assumed to be in S. So obviously this condition is true since V is in S. And then what we do is we can consider the left-hand side of the equation if we were looking at this vector. So we look at this side if it was for this vector right here that we are trying to find out if it's in S or not for. Yeah, so basically you put into the left-hand side, so we have lambda x all squared minus lambda y all squared, and then we actually see that we can factorize out lambda squared, and we actually get this, which is the left-hand side to this condition, so we sub it in, and then we get lambda z all squared, and this gives us the equation right here, and that essentially proves that lambda v is inside S. So we can just say, hence, S is closed on scalar multiplication. So obviously, these slides are also going to be available on our website, so if you can't write everything down right now, don't worry about it. So let's move on to spans. So essentially, spans are when we consider a set of vectors from V1 to Vn, let's call it S, and it's in a vector space V over a field F. So obviously we know what a linear combination is. It's essentially just any vector we can put in the form of a scalar times the first vector, added to a scalar times the second vector, and so on until it's a scalar times the last vector. And these scalars are all under the same field as V. And a span, which can be represented as a span of S, or written as span S, or span and then all of the vectors which are laid out, is the set of every single possible linear combination. So, something that we do need to know is that a span is a vector space of V, and the span S is the smallest vector space, which contains every single vector in S. And the other important thing is that if the span S is equal to the vector space that it's in, then it's called a spanning set. So, how do we use this? So we have a question which gives us a V1, a V2, and a V3, and then a B. And we have to prove that B is in a span of V1, V2, and V3. And then we have a second question, which is if V1, V2, and V3 are a spanning set of R. So what we do is we essentially want to show that it's in a span, so we want to show that there is a linear combination that exists such that the linear combination of V1, V2, and V3 are equal to B. So, of course, we can use an augmented matrix, as we have before, and we just put it into row echelon form, and then the reason we know that there are a solution does exist for this equation is because the solution vector is not a leading column, So a leading column is essentially, if you look from left to right of each row, so in row echelon form, so let's look at this matrix right here. We see, we just look at which non-zero numbers come up first in the row. So for the first row, it would be this 1, and for the second row, it would be this 3, and for the third row, there's no non-zero number. So essentially what that would mean is that there is no leading column which is from the third row, and since we know that the last row doesn't have a leading column, a solution must exist. And if a solution exists for this equation, that means that a linear combination exists and therefore a span exists, such that it's equal to B. So, how do we prove that it's a spanning set for all of R3? Essentially what we do is we have the linear combination and then we let it be equal to a generic vector which can represent any vector in R3. And then we put it into row echelon form as we have right here. And we look at the row with all zeros basically. So essentially what this says is to be a vector inside the span of v1, v2, and v3, we have to have 0 be equal to this equation we have right here. Obviously, that equation is a plane in R3, so it doesn't have every single vector in R3, and hence it doesn't cover all of R3. And that, by definition, makes it not a spanning set. So let's look at linear independence. So say we have a set of vectors, n vectors, which is denoted by S, which is in a vector space V and over the field F. S is known to be linearly independent if and only if the only solution to the equation where the linear combination of S is equal to the vector 0 has this solution. So the only way for the set S to be linearly independent is if the equation right here has one solution, which is given by every single coefficient being 0. Yep, so we have, and what this means is that if it's linearly dependent, there must be a solution where at least one scalar is non-zero. So the other definition, which is more informal, is if we have a vector in S, which can be made up of the other vectors in S as a linear combination, then the set is linearly independent. And if there aren't any such vectors, S is linearly independent. So we have some other properties here. So if the vector 0 is in any set of vectors, then the set is linearly dependent. And two vectors which are linearly independent cannot be equal or parallel. So how do we prove linear independence or dependence? We essentially consider a matrix in the form of this. And there are two ways that we can do it. So the first way is if we put into row echelon form and there are no non-leading columns, then it's linearly independent. And if there are non-leading columns, then the set is linearly dependent. And then the other one is if we have a determinant that is equal to 0 for this matrix, then the vectors are linearly dependent. And if there is a non-zero determinant, then it's linearly independent. So let's look at this example. We have a set of B, which is a set of vectors U, V, and W, and they're linearly independent. And then we have three sets, S1, S2, and S3, defined by these sets. And we essentially have to determine for each if they are linearly independent. So let's look at the first example. The first example is just this set, which is one vector, U minus V, and we just consider a lambda, which allows us to have the linear combination, which is equal to 0. And essentially, what this means is that this vector would have to be equal to each other. Otherwise, it's a non-zero vector, right? but we know that they're linearly independent, so they're not equal to each other. U minus v is a non-zero vector, and essentially what that means is there's only one solution for this equation, which is when lambda is equal to 0. So for the next question, we have a set of two vectors, which is u minus v and v minus w, and we have two scalars which are defined so that we can consider the linear combination of this when it's equal to 0. And we can essentially just rearrange it. So we expand these brackets right here and then put it in terms of u, v, and w, basically, because what we can do is we can use the property that u, v, and w are linearly independent. So the only solution is if these three coefficients are equal to 0, and that basically proves to us that lambda 1 is equal to 0 and lambda 2 is equal to 0. And since the only solution for this equation is lambda 1 and 2 being 0, S2 is known to be linearly independent. So, how about the third set? We can do the same thing where we consider the linear combination when it's equal to 0, and we can do the same thing as the last question. We rearrange it in terms of u, v, and w, do the same trick where all of the coefficients have to be 0, and we actually get the condition lambda 1, lambda 2 and lambda 3 are all equal. So what this means is we can actually choose an example where all of the lambdas, for example, are equal to 1, and we can observe that when we sub in 1 into this linear combination, it does give us the vector 0. This is a non-zero solution, and it's a solution outside of when every single lambda is equal to 0, which means that by definition, S3 is linearly dependent. So, let's move on to bases and dimensions. So, B is a set of vectors over a vector space V. So a basis is defined by if the set B is both linearly independent and a spanning set for V, which means that the span is equal to V. So that would make it so that B is called a basis. And dimensions are actually defined by the number of vectors that a basis has for a given vector space V, and it's usually denoted by a dim and then a V. So essentially we have a set which cannot be linearly dependent if there are more vectors than dimensions in a set. So like if you have 4 vectors in a set of real vectors in the vector space R3, then it cannot be linearly independent. And there's the way that you prove that a set is a basis is by proving 2 of the 3 conditions right here. So the 3 conditions are that the number of vectors are equal to the dimensions, the set is linearly independent, and the set is a spanning set of V. So let's look at this example. You probably don't need to worry too much about the actual way that addition and multiplication have been defined here, but we have a field F which has 4 elements, 0, 1, alpha, and beta, and multiplication and addition are defined in these tables, which just means like if you have 1 and you add it to alpha, you get beta. And if you multiply beta by alpha, you get 1. That's basically what it says. And we also have 3 vectors, b1, b2, and b3, as well as a vector v. So the first is to show that it's a basis. And to show that it's a basis, we first want to prove that it's linearly independent. So what we do is we put it into a matrix and then row echelon form. And we see that it has 3 leading columns, and since there are 3 vectors, we know that there are no non-leading columns, so the set is linearly independent. And we also know that from this 3 right here, the vector space has a dimension of 3, since there are three vectors in the set and three dimensions in F3, as well as it being linearly independent, two of the three conditions are filled. So B1, B2, and B3 must be a basis. And this is for the higher students. This is what I did for my row reduction. You can try it out yourself. It's honestly not that fun to do, but it's right there, so you know. Explain why B1 plus B2, B2 plus B3, and B3 are a spanning set and not a basis. So it's pretty simple to explain why it's not a basis. It has four vectors in a vector space with dimensions 3, so it's not linearly independent. So since the set is not linearly dependent, since the set is linearly dependent, it's not a basis, since one of the conditions is that it has to be independent. So the next thing is we consider the linear combination, and what we can actually do is we can rearrange it to be in terms of B1, B2, and B3, which we know is a basis. And essentially what we've shown is that this is the linear combination of B1, B2, and B3, which we already know is a basis. So since these two are equivalent, the spans of these sets must also be equivalent, and hence this set does span all of the vector space F3. So we have coordinate vectors, which is a topic in 1241, and essentially we have a vector v, which can be represented as a linear combination of a set of bases, and we can put these coefficients into what we call a coordinate vector. So let's just make a coordinate vector of v with respect to the basis b1, b2, and b3. So essentially, you just solve for the linear combination to be equal to that vector, and we should get this as a solution. And from that, we can put it into a vector, which is beta, 1, and alpha. And essentially how that works is, the first coefficient goes into the first component of the vector. The second coefficient is the second component, and the third coefficient is the third component. And this actually works like similarly to how we know vectors. So let's say we had a 2D vectors, and every single 2D vector is defined by two vectors 0, 1, and 1, 0. And if we have 2 and 1, that we know that that's equal to 2 times 1, 0 plus 1 times 0, 1. And this is how we actually derive our coordinate vectors, because it takes 2 of the first vector and 1 of the second vector to make up this vector. Okay, so so we can now move on to linear transformations, which is the second topic. And a linear transformation is also known as a linear map or a linear, all of these mean the same thing, so they're interchangeable, and it's just a function t, which is defined from a domain V. So this is the set that we take the input from, and a codomain, which is a vector space W, which is the set that we take a output vector from. So the function t takes in a vector and outputs a vector, and has two special conditions. The first is that it preserves vector addition, which is if you add two vectors and then you put it through the function, it's the same as putting each vector individually through the function and then adding it afterwards. And then the second condition is that it preserves scalar multiplication, which is you take a lambda v and then you transform it. It's the same as having the individual vector v transformed and then multiplying it by this scalar lambda. So we also say that the linears are functions, so they preserve and they're not closed. And that's mainly because closure is under a set. And how do we prove that it's a linear? Essentially, to prove that it's a linear, we prove that this is true. So we have a linear transformation, which is defined, we have a function defined by the transformation of p is equal to x squared plus 1 times the derivative of p minus 2x times p. And we need to prove that it's a linear transformation. So what we do is first we have to define two generic input vectors. So in this case, our vector space is polynomials of up to power 2 right here. So that's what the 2 means right there. And essentially, that's just like all quadratics, right? So we define two generic quadratics, and then we define two generic scalars. Then we also note that the question requires us to take the derivative, so we have taken the derivative for each of the polynomials we've defined. And now we just construct the thing that we're putting into the transformation. So right here, we just construct what's inside the transformation right here. And that gives us this polynomial, and also we have its derivative. So now what we do is we actually put it into the transformation. So we have the derivative right here times by x squared plus 1, and then the actual thing right here times by minus 2x. So what we can do is we can actually first just expand these brackets right here, and then we can group it up in terms of lambda terms and mu terms, lambda terms and mu terms. And then what we can do is we can continue from our last slide, and essentially we factorize out the lambda and mu, and we can actually, what we can do is we can group them up, right? So we can group up this term with this term and this term with this term, and we actually get the individual vectors being put into the transformation, and that gives us a final line of our right-hand side of the condition. So essentially, whenever we try to prove the condition, we first put in this large vector, and then after we transform it, we break it up in terms of vector addition, and then we take out the scalars, and that should give us our right-hand side. So we know that P2 and P3, they're vector spaces, and they're over the same field R. And since this condition right here is true, T must be a linear transformation. So let's look at a bit of a different example, which is a linear map T being defined by a reflection of a vector in the line y is equal to root 3x. So we have to show what the transformation of 1, 0 and 0, 1 are. And essentially, how a reflection works is you look at the angle that the reflection, so the line of reflection and the actual vector that we're trying to reflect makes, so that's the angle. And then you essentially have the vector rotate in the other direction of the line in the same angle. So these two angles are the same, and then if we're reflecting this vector right here, we get an output of this vector right here. And it's kind of the same for the other thing, other vector. So we have the vector 0, 1, and it makes an angle of 30 degrees with this line right here. So to reflect it, we rotate it once 30 degrees in this direction, and then we rotate it again. So it's rotated twice to get this new vector, which is our reflected vector. And essentially what we've noticed is that for our first reflected vector of 1, 0, there's an angle of 60 here, so in total an angle of 120 overall. And we just chuck it into our polar coordinates, which you should have learnt from like complex numbers, and that should give us this vector right here. And we do the same thing here, so we know that our reflected vector has an angle of 30 degrees here. We put it into our polar coordinates, and then we should get that vector right here. So now what we can do is we actually use the fact that a transformation, which is defined by a matrix times a vector, is always a linear map. And we can put this into something called matrix representation theorem, which basically means any transformation that we have can be put in a matrix times a vector. And the matrix is made up of columns of the first basis being transformed, and then the second basis being transformed, and then up to the nth basis being transformed. So we have a linear map, which we know it's transformed, like defined by this reflection, and we have a we need to find the matrix A for this transformation. So from our last question, first we know that the basis of R2 is given by 1, 0 and 0, 1, and we've actually found out what these are transformed in the first part. So what we do is we put it into a matrix. So here we see that the first basis being transformed is the first column, and then the second basis being transformed is the second column. And that's how it's done. So now, we want to find the vector 4 and 5 being transformed. So what we do is we can essentially just expand it by the conditions of a linear map. So we have vector addition right here, and we can take out the scalar because of preserving scalar multiplication. And then we get left with two vectors that we already know from part A. We sub those in, and that should give us an answer right here. But something else we can do is from part B. So alternatively, we know that the transformation is just this matrix times the vector. So we multiply the matrix that we found in part B by the vector, and that should also give us the same answer right here. So for our next question, we have two vector spaces, V and W, and we have a linear transformation from V to W. And then we have n vectors being defined, so V1, V2 up to Vn. And essentially we need to prove that V1, the transformation of V1 and the transformation of V2 and the transformation of up to Vn is linearly independent. So if that is true, then we have to prove that the original vectors that we transformed are linearly independent. So let's look at the first question. And what we can do is we can consider the linear combination of V1 to Vn when it's equal to the vector 0. And what we actually see is that first we know that the vector 0 is of the codomain W is equal to the transformation of the 0 vector in V. And this is just a basic fact that we should know. It's proven in your notes as well. We can substitute this linear combination that we've created in here, and we can essentially break it up in terms of individual lambdas and t's of vectors, as we have through the use of linear maps laws. And what we actually find is that since these vectors are linearly independent, as seen in the question right here, the only solution to this equation is having all of the lambdas be equal to 0. So that automatically means that since we actually took the lambdas from this equation right here, that equation also only has the solution of lambda being 0. So what we've shown is that v1 to vn are indeed linearly independent. So for our next question, it's the other way around. So we know that these vectors are linearly independent, and then we want to show its transformations are linearly independent. So we actually know that this is false, and what we can do is let's just look at an example in which it doesn't work. So first, what we know is that we have these which are linearly independent, but the transformation can have a vector v which isn't equal to the vector 0, which has an output of the vector 0. So there are cases where this vector v, which isn't 0, is a linear combination of n vectors. So that means that these vectors are not linearly independent, and that's like what I would probably write in an exam. But just to like give you an example of how this works, we can define this linear transformation, and essentially we know that these two vectors are linearly independent, and we have and then we can consider the transformation of this vector, which we know is equal to 0, since 1 minus 1 is 0. And then what we can do is we can actually put this vector in terms of our two vectors right here. And what we've shown is that there exists a non-zero solution for the linear combination of the transformations when it's equal to 0. And that essentially says these two vectors are linearly dependent. So now we can move on to kernel and null space, which is essentially we have a kernel which is defined to be the set of all vectors such that if you put it into the transformation, an output of 0 happens. And in the case of a matrix, if you multiply it's a set of all vectors where if you multiply it by the matrix A, you get an output of the 0 vector. And you can kind of think of it as like the roots of a linear transformation, since a linear transformation is a function. And something else is that the kernel is always a subspace of V, and then we have nullity. And nullity is the dimensions of the kernel, and it's shown to be like a nullity of the transformation T or nullity of the transformation of A. And the kernel is defined like, it uses the notation Ker, so it's CER of T or CER of A. So let's look at this maple output, and the question is to find a basis for the kernel of A. And to find a basis, we want to find every single vector such that the matrix A is equal to the 0 vector. And something that we know is that the maple output has already solved it for us. So we don't need to find the kernel in this case. That is the kernel. So this vector right here is the kernel. But, yep, so we have to, generally to find the kernel, we have to solve the augmented matrix, where the matrix is equal to the 0 vector, and maple has done this for us. So we essentially just need to define our scalars. So we have underscore T3 and underscore T5 being equal to lambda and mu. And the reason I've done this is because what maple does is in its outputs, the scalars are given by these terms. So those are the parametrics that maple uses, and it's kind of confusing. So we're just putting it into terms that we know better. And essentially what you do is you take the solution of the kernel, and then you break it up into its individual vectors, and we see that it's actually equal to lambda times the first vector and mu times the second vector. And so we know that, first we know that these two are linearly independent because the first vector has a component in the third component, whilst it's 0 in the second vector, and the second vector has a component in the fourth component, whilst it's 0 for the first vector. So they're linearly independent, and they also have a span which is making up all of Ker A. So we can say that it is indeed a basis of the kernel, since it's linearly independent and it's a spanning set. So now we have the image, which is essentially every single output vector which is possible when transforming some vector v in T. And an image for matrix A is just every single vector output which is created by some vector x when you multiply it by the matrix A. And it's kind of just like the range of a linear transformation, and the image of a linear transformation is always a subspace. So rank is similar to nullity, but instead rank is the dimensions of an image. So rank is notated by rank, and image is notated by IM. And so to find the rank and nullity, essentially we put the matrix that we're trying to find for into row echelon form, and we count how many leading and non-leading columns there are. So the amount of non-leading columns there are is the nullity, and the amount of leading columns there are is the rank. And to find the kernel and basis, the kernel, you just solve this augmented matrix through back substitution, and for the basis of an image, you put it into row echelon form, and the corresponding vectors of the original matrix which are leading is how we find the basis of an image. We'll see how we do this later, so don't worry if you don't get it at first. And then we have rank nullity theorem, which basically says the rank plus nullity is equal to the dimension of the vector space that we're in, or the rank on nullity is equal to the number of columns in the matrix. So we have a matrix D right here. It's a 3×3, and we want to find every single vector which is B, which is belonging to the image of D. So the way we do that is it's essentially just seeing if it's like in the span. So you solve it by letting the solution vector be B, and then putting it, essentially we just multiply these two, 3 by the second row and 2 by the third row to see that we can actually have them be equal. And that gives us the condition that 3 times B2 is equal to 2 times B3. And this is the plane that contains every single vector B that belongs to the image D. So now we need to find a basis for the image. And as we've said, we put it into row echelon form, and we see that these two vector columns are leading. So we have 2 leading columns. Oh, whoops. So these 2 are leading columns, and since they relate to these 2 columns right here, those actually become the basis vectors of our image. Okay, so, and now we want to find the rank and nullity of our matrix D. So the rank is the amount of the dimensions in D, and we know that the image of D has a basis of 2 vectors. So since there are 2 vectors, by definition, there are 2 dimensions. And so we have rank equal to 2. And we also know that D has 3 columns. So by rank nullity theorem, we can actually say that the rank plus nullity is equal to the amount of columns. So 2 plus nullity is equal to 3. And we can solve for nullity, which is 1. And now we want to find a basis for R3, which contains B. which is essentially we have the basis of D, which is given by B right here, which is these two vectors. But we know that two vectors can only span a plane when we consider its linear combination, because the plane would be something like this. So essentially we need a third vector which travels in a direction that is not traveled by this plane. So what we can do is we can actually take the cross product of these two vectors, and we would get a vector which is perpendicular to both. And since that vector is perpendicular to both vectors in the basis, it travels in a direction which neither of these travel in, and hence this is a third vector to the basis which spans R3. And this is the end of my section, so that's linear transformations. I'm going to hand it over to the person who's presenting this, which is the lovely Lachlan Tobin.
Hello.
Take it away.
Okay, I'll just get started then. So the next component is looking at eigenvectors and eigenvalues. So we'll start with a brief definition. So if A is an n by n matrix, and lambda is a scalar, and V is a non-zero vector in some field, some vector space, then if AV equals lambda V, in other words, when you put the vector V into the matrix A, you get a scalar multiple of the original vector, then you can say that lambda is an eigenvalue, and V is the corresponding eigenvector for that matrix A. So geometrically, in 2 dimensions at least, you can think of it as a vector. If it's an eigenvector, when you input it into the linear transformation A, what you get is a scalar multiple of that initial vector. In other words, it's just going to stay on its span. So in other words, if you had a vector on a line, if it's an eigenvector, then that vector is just going to be scaled along that line. So to actually compute the eigenvalues and then the eigenvectors of some matrix, what you do is solve something called the characteristic polynomial. So our characteristic polynomial is this polynomial defined by the determinant of A minus lambda I equals 0, where I is our n by n identity matrix. Lambda is going to be our eigenvalue. Eigenvalue. And then to find the corresponding eigenvector for any eigenvalue, what you do is solve the equation A minus lambda I multiplied by V equals to 0, where V is non-zero because trivially any zero vector, if you input it into a matrix A, what you get is a zero vector back, which means that it would be an eigenvector if we didn't change our definition. So some extra information here. The set of eigenvectors for any matrix A is known as the eigenspace of A. But that's not really that important. So let's move on. If we are dealing with an n by n matrix, right? If you actually find what the characteristic polynomial is, what you'll get is a polynomial in terms of lambda in degree n, which means by the fundamental theorem of algebra, we should have n solutions to this, only if we account for real n complex solutions and also count solutions for their multiplicity. Also, if we are dealing with distinct eigenvalues, so if we solve an n by n matrix and we find it to have n distinct eigenvalues, then we should have a set of n linearly independent eigenvectors. So diagonalization. If we're dealing with an n by n matrix with n linearly independent eigenvalues, then we can write two matrices, M and D. So M is going to be the matrix whose columns are defined by our eigenvectors. So if we have n eigenvectors, then we should have n different columns. And D is a diagonal matrix with the diagonal entries equal to the corresponding eigenvalues. So if lambda 1 is the eigenvalue corresponding to the vector v1, then what we should get for the diagonal matrix is a matrix with diagonal entries lambda 1, lambda 1, all the way up to lambda n. And then we're able to write A, our original matrix, in terms of M, D, and M inverse. So you can see here that A would be equal to M multiplied by D multiplied by M inverse. And the process of finding the matrices M and D is known as diagonalization, because we can express A in terms of a diagonal matrix D. And diagonal matrices are very nice to work with because they multiply nicely, because you can just multiply the diagonal entries instead of having to do your normal procedure for matrix multiplication. So you can see here, theorem 3, if A is diagonalizable, if and only if it has n linearly independent eigenvectors, and that comes from our ability to write the matrices M and D. To actually write M, we're going to need n linearly independent eigenvectors. So let's move on to a question. So if we're working with some matrix C, the first part is to find the eigenvalues of C, and for each eigenvalue, find the corresponding eigenvector. So to actually do this, remember the procedure. We said that the eigenvalues were the values of lambda, which which are the solution to the characteristic polynomial, which was the determinant of C minus lambda I. Equals to 0. Right? So to actually do that, let's write the determinant of C minus lambda I. In this case, it's going to be the determinant of this matrix, 1 minus lambda, 2, negative 2, 5 minus lambda. And then actually expanding out that determinant, what we should get is the quadratic lambda squared minus 6 lambda plus 9. And you can see that factorizes into lambda minus 3 whole squared. Minus 3 whole squared. And you can see that for this to equal 0, the only value of lambda we get is lambda equals 3. All right, so then our eigenvalue, or our only eigenvalue for this matrix C, is lambda equals 3. And now to find the corresponding eigenvector, remember the process. We solve the equation C minus lambda I multiplied by V equals to the 0 vector. So in this case, we replace lambda with C, and then write the vector, the matrix C minus 3i, which is going to be negative 2, 2, negative 2, and 2, right? And actually, remember, we're trying to solve for when this matrix multiplied by V equals 0. So to do that, we can just augment it by the 0 vector and then row reduce it. So actually performing our row reduction, we should get the solution V equals some parameter multiplied by the vector 1, 1. So you can see for our eigenvalue, lambda equals 3, the corresponding eigenvector was T, 1, 1. So now, this is our only solution for the eigenvalue and the corresponding eigenvector for the matrix C. Now, the question previous, part 2, asked, is C diagonalizable? And the answer is no, because in this case, for it to be diagonalizable, we need 2 linearly independent eigenvectors. But you can see that having solved for the eigenvectors, we only get one eigenvector and one corresponding eigenvalue. So there's no way we're able to write the matrices M and D. In other words, we can't diagonalize it because there don't exist matrices M, D, and M inverse that we can write the expression C equals M inverse D times M. And you can say, therefore, that C is a defective matrix. So to actually evaluate the power of matrices, this is where diagonalization comes in handy. So you can see by expressing a to the power k and multiplying it out k times, the M inverse M terms canceled out, and we can see that a to the k is simply equal to M times d to the k multiplied by M inverse. And the reason why that's helpful is because the matrix d to the power k, or in other words, taking the diagonal matrix to the power k, is as easy as just taking each diagonal entry to the power k, because multiplying these diagonal matrices is quite nice. So a question here from a 1241 paper was, if we have a real n by n matrix A with n distinct eigenvalues, and then there would be corresponding n in linearly independent eigenvectors, and it can be expressed in the form M inverse dm. So in other words, the matrix A can be diagonalized. Now the first part of the question is it says, write the characteristic polynomial p of x of A in the form of a general power n polynomial. And then it says to replace the variable x by the matrix D and replace the constant a0 by a0 multiplied by I, where I is the n by n identity matrix. Now it asks us to prove that P of D equals to the n by n zero matrix. So to do this question, we'll start out with doing what they ask us to do. So we say the characteristic polynomial can be written in some sort of general form. And we know because of our definition for eigenvalues, the set of eigenvalues, lambda 1 up to lambda n, should be the n roots of this characteristic polynomial. Now, doing as they say again, we're going to replace x with d and replace a with a0 I. And now we have some sort of matrix polynomial, I guess, in terms of d and powers of d. Now, we need to prove that this is equal to the zero matrix. So first thing to note is that every expression or every matrix in this polynomial, they're all diagonal matrices. Because D is a diagonal matrix, taking the power of a diagonal matrix gives us another diagonal matrix, and multiplying by a scalar wouldn't change that. Now we're going to have to consider the entries or the diagonal entries of this entire expression, and we want to prove that each entry is equal to 0, right? So you can see that d to the power n, right? That would be equal to lambda 1 to the power n, lambda 2 to the power n, and all the way up to lambda n to the power n, right? Where lambda are our eigenvalues. And these are the diagonal entries. Every other entry in the matrix should be 0. I'm just not going to write them out fully. So you can see that this is true for all the powers of d. And if I just multiply it by some constant, that constant is just going to go into each diagonal term. So what that means is, for this whole expression, P of D, right, the kth entry of this, the kth diagonal entry of this matrix should be lambda to the power k, lambda k to the power n plus n minus 1, lambda k to the power n minus 1 plus all the way up to a1 multiplied by lambda plus a0. Right? So we'll move on to the next slide. The kth entry should be the characteristic polynomial, except replace x with lambda k. And we know that because each of our eigenvalues are the solutions to the characteristic polynomial, all of these diagonal terms should be equal to 0. And what that means is when we sort of put that matrix D in, what we should get is just the 0 matrix. So every entry in the matrix should be 0. Any questions there? Okay, moving on then. The second part, was to prove that P of A equals 0. So the previous part we proved P of D was equal to 0. Now we want to prove P of A equals 0. And to do this, we're going to realize that A to the power K is just equal to M inverse D to the power K multiplied by M. Now, substituting that expression into the characteristic polynomial gives us this very long expression here. But we can notice that that's just the same as our P of D polynomial, except each term is multiplied on the outside by M inverse and M. And we can factorize those out leaving us with M inverse multiplied by P of D multiplied by M. And because P of D was equal to the zero matrix in our previous part, then this whole expression should also equal to the zero matrix. So now we've proven that P of A equals 0. The third part of this question was to use our previous result to show that the matrix 2, 4, 1, negative 1 satisfies A squared equals A plus 6i. So you can see for this question, we're just going to use our previous result, and that is P of A equals 0. In other words, A should be a matrix solution to the characteristic polynomial. So for this question, part C, all we have to do is find the characteristic polynomial and substitute A in, right? And that will be equal to 0. So again, to find the characteristic polynomial, that was the determinant of A minus lambda I. So actually determining it, we're going to expand out our determinant, and we should get lambda squared minus lambda minus 6. And now we know that if we replace 6 with 6i and lambda with A, this should be equal to the 0 matrix by our previous results. And that means that A squared equals A plus 6i, just rearranging a little bit. So we can actually apply our knowledge of eigenvectors and eigenvalues to solve systems of differential equations. So here's a theorem here, or proposition. If we have an n by n matrix A and some differential equation, dy dt equals lambda, ay, where a is some vector function, then the solution to this, or one solution to this, will be y of t equals e to the lambda t multiplied by v, where lambda is one of the eigenvalues of our matrix A, and v is one of the corresponding eigenvectors for our matrix A. And now, if we had n linearly independent eigenvectors, then what we should get is n different linearly independent solutions, and our general solution is going to be just a linear combination of all those solutions. So that's what we have here. And we're introducing constants alpha 1, alpha 2, up to alpha n to write our general solution. So let's go ahead and actually apply that in a question here. So we have a system of two differential equations in two functions, x and y, right? So to actually solve this, what we want to do is write this as a vector differential equation, and then we can apply our proposition from the previous slide. So you can see here that if I had some matrix, if I had some matrix 4, negative 2, 1, 1, and I multiplied that by the vector xy, what I would get is the new vector 4x minus 2y x plus y. And I want this to be equal to dx dt, I want this to be equal to dx dt and dy dt, right? Because this is an equivalent way of writing our differential equation. So I can let y, a new vector y, equal to x, y, right? Where x and y are our functions of t. And that means what we have is an equivalent system, I guess, to our two differential equations. And that is dy dt equals ay, where a is equal to 4, negative 2, 1, 1, and is our coefficient matrix. And y, the vector y, is equal to xy, with xy being our two functions that we're interested in. So now, remember this, the method to solving this differential equation. First, we need to find the eigenvectors and eigenvalues for our matrix A. So again, to do that, the process is solving the characteristic polynomial, a minus lambda I, and actually just expanding that determinant out and factorizing, we should get lambda minus 2, lambda minus 3. And that's equal to 0. How do we fix this? Yep. So that gives us lambda equals to 2 and lambda equals to 3. as our two eigenvalues. And now the corresponding eigenvectors, remember the process here was just to solve a minus lambda I multiplied by v equals 0. They should be t11 and t21, and you can check that for yourself. So now we can see that two linearly independent solutions to this system should be y equals e to the 2t times 1, 1, and y equals e to the 3t, 2, 1. And these are just specific solutions. This is not our general solution just yet. Remember, in this case, e to the 2t, 1, 1, 2 is our eigen value, and 1, 1 is our eigenvector. So now, remember, our general solution was going to be the linear combination of these two solutions. And what we do is we just introduce two new constants, a, b, and we write this. Now, we're not finished just yet because the question asks for the solutions for x, y, not the solutions for the vector y. So now we remember that y equals to x, y. And now x is just going to be the top row of our vector here, and y is going to be the bottom row of our vector, giving us x equals a e to the 2t, and y equals a e to the, plus 2b equal to the 3t, and y equals a e to the 2t plus b e to the 3t. But our methods here that we've just gone through can also be applied to solving higher order ordinary differential equations. For example, second order differential equations. We learned methods to solve them in the calculus part, but we can also use eigenvectors and eigenvalues to solve this system. And to do that, there's just one trick involved, and that is realizing that if we set y1, so some new function y1 equal to our original function y, and some new function y2 equal to dy dt, what we have is the original differential equation, which remember was y double dash minus 6y minus 24y, so 24 equals, 24y equals 0. Oops. Oops. Yep, 24 equals 0. You can see that if we're looking at what happens at y1, right? We know that dy dt equals y2. So therefore, dy1 dt equals y2, just using our known expression for y1. And similarly, if we rearrange the original differential equation, we can see that y double dash equals to 6y dash plus 24y. Right? And that means that d squared y over dt squared equals 24y plus 6y dash. In other words, dy2 dt equals 24y1 plus 2y2. And now we have a system of two differential equations, which was kind of exactly the same as what we did in the previous question. All we have to do now is write the coefficient matrix A, and then write it in the form of dy dt, where y is some vector function, equals ay. Ay. Right? So in this case, our coefficient matrix A should be equal to 0, 24, 1, 2, and y, our vector, should be y1, y2. Now, actually solving this coefficient matrix for the eigenvalues and the corresponding eigenvectors gives us lambda equals 6 corresponds to the eigenvector alpha 1, 6, and lambda equals -4 corresponds to the eigenvector alpha 1, -4. And now remember that our solution, or at least two specific solutions to this equation, should be y equals to e to the 6t multiplied by 1, 6, and y equals to e to the -4t multiplied by 1, negative 4. So now we know that our general solution is the linear combination of these two specific solutions, giving us a general solution of C e to the 6t, 1, 6, plus D e to the negative 4t, 1, negative 4. But the original question was not to find some solution y, or the vector y. It was to find what is just y in general, right? If it's the solution to y double dash equals 6y dash plus 24y. Now, to actually find what y is equal to, we just look at the first row of this, because remember we said that the vector y was y1, y2. The first row should just be c e to the 6t plus d e to the negative 4t. This should be t here. Anyway, now that's our general solution for y, and that's how we solve second-order differential equations using eigenvectors and eigenvalues. So moving on to the next, or the last component of the course, which is probability and statistics. So we begin with a definition of probability. So it's a bit of a formal definition, but probability on a sample space S, well, it's a function that goes from the elements of the sample space to the real numbers, right? So the probability of an event in the sample space happening is a real number, but it's important that that number is between 0 and 1. The probability of nothing happening is 0, and the probability of something across the whole sample space happening is 1. Now, if we have two disjoint sets, so they have no overlap, then the probability of A or B occurring, right, is the probability of A plus the probability of B. But a more general expression for this is the probability of A or B is the probability of A plus the probability of B, subtracts the probability of A and B, so their intersection. Additionally, if we're looking at the probability of some complement, that's 1 minus the probability of the original event. If A is a subset of B, then the probability of A is less than or equal to the probability of B, and the probability of every event occurring in that subspace as we sum them up, that should equal to 1. Now, conditional probability here. So if A and B are events in a sample space S, such that the probability of B is non-zero, then the probability of A occurring given B has occurred is the probability of A and B divided by the probability of B. And this comes from our tree diagram here. So generally, when we're working with conditional probability, it can make the question a lot easier if we actually write out our tree diagram. So you can see that for these four outcomes, A and B, A complement and B, etc., there are four different ways that we can get to that event. If we start with B having occurred first, so B or B complement could have happened, and then under each of those two cases, A or A complement could then further occur. So the three important rules helping us find probabilities, when we're working with conditional probabilities at least, is first the multiplication rule. So the probability of A and B is the probability of A given B multiplied by the probability B, and also vice versa. The total probability rule. So if B1 up to Bn completely partition S, right, then the probability of A is the sum of probability of A occurring under all the events B1 up to Bn. And to actually get these little expressions here, we use the multiplication rule. And that gives us the total probability rule. And the last one is Bayes' rule. So the probability of Bk occurring given A has occurred is equal to this here. And normally in the expression of Bayes' rule, the probability of A is written as it is using the total probability rule. So summing it out over all the possible cases B1 up to Bn, as long as they partition S. So our last definition here is mutual independence. So events A and B are mutually independent if the probability of A and B is the probability of A multiplied by the probability of B. That's the same thing as saying the probability of A is equal to the probability of A given B. In other words, the given part of that statement is redundant because they are mutually independent. So let's go ahead and apply this onto a question. So on the basis of the health records of a particular group of people, an insurance company accepted 60% of the group for a 10-year life insurance policy and rejected the others. 10 years later, the company examined the survival rates for the whole group and found that 80% of those accepted the policy had survived the 10 years, while 40% of those rejected had survived the 10 years. So now the question is, if a person from the original group did survive 10 years, what is the probability that they had been refused a life insurance policy? So what we're dealing with here is a problem about conditional probability. So let's say the event that someone survives is S. So this is the event that they survive. And A is the event that they were accepted. So now we want to find the probability that they were accepted given that they survived. Given that they, the probability that they were not accepted given they survived. So to actually do this, let's write out our expression. Or actually, first thing we should do is actually write out a tree diagram. Because if we write out the tree diagram, then we can see clearly all of our different outcomes and the probabilities associated with them. So let's just look where these numbers come from very briefly. So the probability that someone was accepted in the first place was 60%, right? Because 60% were accepted, and correspondingly 40% were not accepted. Now, let's look at the case where someone was first accepted. So out of the group that was accepted, 80% survived, right? Giving us our 0.8 for the outcome that they survived and were accepted. That means that 20% did not survive, giving us the outcome that did not survive and they were accepted. And using the same logic, we could derive an expression for all our other outcomes. So now, to actually find this probability that they did not survive, were not accepted given they survived, first let's write out an expression for this conditional probability using our definition of conditional probability. So it's important to look at what we know and what we don't know. We do know the probability that they were not accepted and survived. That comes from our tree diagram that we just wrote out. So to get to the case where they were not accepted and survived, you can see that it's going to be 0.4 times 0.4, right? So that gives us this top probability is 0.4 squared. But we don't know the probability someone survived in general. However, what we do know is that the events someone was accepted and someone was not accepted partition S. So to find the probability of S, we can use the total probability rule. So expanding that out using the total probability rule gives us 0.8 times 0.6 plus 0.4 times 0.4, and that gives us the total probability that someone would was not accepted given they survived, equal to 0.25. So now, moving on to a little bit more of a difficult question. Say we have two urns, right? The first urn contains 3 red balls and 4 blue balls. And the second urn contains 4 red balls and 2 blue balls. Now, 1 ball is drawn at random from the first urn and placed into the second urn. And now we draw a ball at random from the second urn. So, again, the first thing that we should draw, because we have a small amount of cases, a small amount of total possible outcomes, it makes sense to draw a tree diagram. So this is our tree diagram here for this case. So let's look at where this comes from briefly. Again, from the first urn. So just to be careful here, I'm denoting you've gotten a red from the first urn by R1, and you've gotten a red from the second urn by R2, same with blue. So the probability of getting red from the first urn is just 3/7, because we have 7 total balls. Now, let's look at the first case that we've drawn a red ball. We've added a new red ball to the second urn, so the probability that we draw red from the second urn is going to be, let's see, originally we had 4 red balls. Now that we've added a red ball, we have 5. That gives us 5/7, and that's the same for every other outcome. We just use the same process there. Now we want to find the probability that the ball drawn from urn 2 is blue. So in other words, the probability of getting blue from the second urn. And you can see here that blue, or the case of getting blue from the second urn, is partitioned by getting red or blue from the first urn. So in this case, to find the probability that we draw blue from the second urn, it makes sense to use our total probability rule. And actually applying that total probability rule, remember we can expand it out like this. So we can expand it out, and just multiplying our terms should give us 18 over 49. So let's look at the second question. Given that the ball drawn from the second urn is red, what is the probability that the ball transferred was blue? So in other words, this here is going to be the probability that probability that we get blue 1 given we've gotten a red 2, right? So to do this one, it makes sense to apply Bayes' rule. So actually applying Bayes' rule, right, we can see that the probability of getting blue 1 given we've rolled some red, or we've drawn some red 2 from the second urn, we can expand it out using Bayes' rule. And we actually know all of these probabilities, right? We know the probability that we've gotten red 1 given we've drawn a blue 1, etc. From our tree diagram, right? All of those probabilities are given here. So now it just becomes a matter of substituting our numbers in, and we should get 16 over 31. And the third part is, let A be the event that the ball drawn from the first urn is blue, and B be the event that the ball drawn from the second urn is blue. So the question is, are A and B statistically independent? So you can see that the answer should obviously be no, because whatever outcome you get from the second urn is inherently dependent on whether you draw red or blue from the first urn. So intuitively, we can say that the answer should be no. You can prove that using our definition of mutual independence. So you can see that the probability of A and B was not equal to the probability of A multiplied by the probability of B. So moving on from probability to random variables here. So the formal definition of a random variable is a function that maps from the sample space to the real numbers. In other words, it's a way that we can map the outcomes of a random experiment to some real number. For example, if I flipped a coin, I would map the outcome heads to the number 1 and the outcome tails to the number 0. And some random variable will be discrete if its image is countable. In other words, all the set of function values, or the set of random variables, possible random variables, is a discrete number. Moving on from that definition to the definition of the cumulative distribution function. So it's a sum function that outputs the probability of our random variable being less than some variable x, right, that we decide to pick. And it has some nice properties. It is non-decreasing. If A is less than or equal to B, then the probability of A being between A and B, so x being between A and B, is f of B minus f of A. And as we take the limits to negative infinity and infinity, we should get 0 and 1 respectively. Now, a probability distribution function is a description of all the total probabilities associated with the random variable x. And we can denote the kth, or the probability of the kth outcome occurring as pk, and that is the probability that the random variable is equal to some outcome xk. So a collection of real numbers can only be a probability distribution if each probability is non-zero, greater than or equal to 0, and as we sum all the probabilities, right, over the entire sample space, we should get the number 1. And now we can express the cumulative distribution function, or CDF, as being the sum of all probabilities less than or equal to some variable x. So the reason why we introduce random variables is because this allows us to calculate the expected value or the variance. So the expected value is the weighted sum of all the outcome values. So it's the sum of all of the outcomes, xk, multiplied by the probability of that event occurring. And that's also denoted mu, or the mean. Now, if we apply a function to the random variable to get some new random variable, then that's the same as applying a function within the sum. And that is handy when we're trying to calculate the variance, because the variance is defined as the expected value of the squared deviations from the mean. In other words, that's sort of saying that's the average of all the squared distances of each outcome from the mean. So it's a measure of spread. And that comes, or at least our formula for the variance of x is the expected value of x minus mu squared, giving us sigma squared. But that can be calculated more easily, I guess, by using this expansion. And you can see that e of x squared, e of x squared is going to be equal to, we take the sum of all x squared multiplied by the probability, and we take that over all k values. And also, the standard deviation is the square root of variance. So given a, b as some real constants, if we scale the random variable, then you can see that the expected value, variance, standard deviation behave fairly nicely according to this. So now let's move on to a question here. So given we have two not necessarily distinct vectors, v1 and v2, chosen at random from this set. So the set of all vectors whose components come from the set -1, 0, 1. Now define A to be the event that v1 and v2 are linearly independent. So remember our definition of linear independence. That's just saying that in this case, the vectors that we choose won't be scalar multiples of each other, right? So now the first part is to find the probability that given we pick two random vectors from this set, that they are linearly independent. So you can see, first of all, to do this, we're going to have two numbers, right? The number of ways that we can pick a linearly independent vector. So number of ways to pick vectors that are linearly independent, right? And also the total number of vectors that could be formed. Number of vectors. So you can see that in the set S, right, we have three choices for the components x and y. So then there should be 3 squared ways that we can make a vector in S, right? That's just looking at, we have 3 choices for x, 3 choices for y, so multiply them together to find the total number of ways, giving us 9 vectors that could be formed in S. If we're picking 2 vectors, right, v1 and v2, there should be 9 times 9 ways that we can pick 2 vectors, giving us 81 different ways that we can pick v1 and v2. Now we want to find the number of ways that we can pick linearly independent vectors. So the best way, or the most intuitive way, I guess, of doing this, because there's only 9 vectors in S, it makes sense that we are able to write out every single vector that we can form. It won't take too long. So actually writing out those vectors gives us the set of these vectors here. So you can see, importantly, these vectors actually come in linearly dependent pairs if we just first exclude the 0 vector. The reason why is because the 0 vector is linearly dependent with any other vector because it's 0 times that vector. So let's just consider every other vector except the 0 vector. You can see that these come in linearly dependent pairs, right? So now, let's find the number of ways that we can pick a pair of linearly independent vectors. So there are 8 choices for the first vector. So say I choose any random vector in this set of 8 vectors, for example, the vector 1, 1, right? Now, the only choice, or the only 2 choices that would result in a linearly dependent pair is if I picked 1, 1 again, or -1, -1. Every other vector will be linearly independent with the vector 1, 1. So that gives us 6 choices for the second vector. Yeah. So now this should just become 8 times 6 equals 48. So now the probability should be 48 over 81, which gives us 16 over 27. And that's our answer for part 1. So now let's look at what part 2 was asking us to do. So define the discrete random variable to be the dimension of the span of the two vectors, and complete this table for the probability distribution of this random variable x. So in this case, right, if the dimension of the span was equal to 2, those vectors had to be linearly independent, because if I choose 2 linearly independent vectors from that set, they should span 2 dimensions. And so therefore, we already know the probability of x equaling 2. That's just going to be 16 over 27 like we found in the previous part. Now we have to find the probability that the dimension of the span of the vectors is 1. Now that's only true when the vectors span a line. In other words, the vectors are scalar multiples of each other. So actually, looking at our set of vectors, right? Again, our set of vectors was given here, right? We want to choose or find the number of ways that we can choose 2 vectors such that they are scalar multiples of each other. So first, I'm just going to ignore the 0 vector again. So there are 8 choices for the first vector. So remember they came in linearly dependent pairs, right? You can see that if I first ignore the choice of the 0 vector first, there are 8 choices at the start. And out of these 8 choices, if I pick, so say I picked 1, 1, right? So 1, 0. Now, there are 3 other vectors I could pick such that they are linearly dependent or scalar multiples of each other. And that would be 1, 1 itself, so 1, 0 itself, negative 1, 0, or the 0 vector, right? And now I just add another 8 choices for when I pick the 0 vector first, right? So now this should give us 8 times 4 equals 32 different ways that I can pick linearly dependent vectors such that they are scalar multiples of each other. And now dividing by 81, the probability of x equaling 1 is 32 over 81. And now, what about the probability of x equaling 0? So in other words, the dimension of the span of the vectors is 0. That's only true if I pick the 0 vector twice. There's only one way of doing that, which gives us the probability of x equaling 0 being 1 over 81. So now, just completing out our table, we should get this distribution of probabilities. And now, the last part of the question is probably the easiest part, is to find the expected value and the variance. So remember our definition of expected value. That was just the sum over all k of k multiplied by the probability of x equaling k. Just expanding that sum out, we should get 128 over 81. Now, the second part was to find the variance. So remember our shorthand expression for the variance, that was e of x squared minus mu squared. Finding the e of x squared, you remember you sub k squared, or the sum of all k squared multiplied by the probability of x equaling k. Expanding that sum and subtracting away the square of the mean, which we found in the previous part, we should get 1,760 over 6,521. So let's move on to Bernoulli trials and processes, which are leading up to the binomial distribution. So a Bernoulli trial is an experiment with 2 possible outcomes, success or failure, with the probability of success being p, the probability of failure being 1 minus p. And a Bernoulli process is a sequence of identical Bernoulli trials where each trial is mutually independent. So now, if x is a random variable indicating the number of successes in a Bernoulli process, the probability of x equaling k is n choose k multiplied by p to the k multiplied by q to the n minus k. That comes from, we have k successes, so we need to pick those k out of n, so that's where the n choose k comes from. Then we multiply by p to the k because we succeed k times, and then we fail n minus k times, giving us q to the power n minus k. So a binomial distribution is given by the following probability distribution function, n choose k, p to the k, 1 minus p to the n minus k. And so a binomial distribution models, or is the distribution for this Bernoulli process. So in this case, k is going to be the number of times that we succeed, and p is the probability of success, and n is our total number of trials. So using this expression for the probability distribution function, we could determine the expected value, and we could also determine the variance, so the NP and NPQ respectively. Another discrete distribution from Bernoulli processes is the geometric distribution. So whereas the binomial distribution modeled, if we have n total trials, we have k successes, the geometric distribution models the number of trials it takes before our first success. So in this case, with a probability p success, it takes k trials before our first success. And we can show that the expected value would be 1 on p, and the variance would be q on p squared. So a sign test is just a way of deciding whether two sets are purely different because of chance or because there is evidence of an actual statistical difference between the two sets. So we want to find the probability of the two sets being as different as they are due to pure chance, right? And to do that, the first step is to count the number of instances. So in this case, at least, we're trying to show that, I guess, or determine whether algebra students are better than calculus students. So the first step is to count the number of instances where algebra is strictly greater than calculus. So just going through that here, we can see that that occurs at all these instances, right? So that gives us 10 different times where algebra is strictly greater than calculus. So that's the first step. Our second step is to look at all the total cases where there is a difference between the two sets. So we also count for where algebra is strictly less than calculus. And that occurs here. It occurs here and here, right? So in other words, there are 10 times when algebra is strictly greater than calculus, and a total of 13 times when algebra and calculus are non-equal. So now what we do is we say, or assume at least, that this was due to pure luck, and we find the probability. If it was due to pure luck, the number of times where algebra is greater than calculus, that should be equal to a half. I guess the probability of algebra being greater than calculus should be equal to a half. And so this becomes a binomial distribution with 13, n equals 13, because there are 13 times where they are strictly different, and a probability half. And now the probability that algebra is greater than calculus more than 10 times, just expanding that out, is 0.0461. So there is a 4.61% chance that algebra is greater than calculus, given that it's pure chance that algebra was greater than calculus. And normally we take something called a significance level, called 5% in this case. So wherever this probability of it being due to pure chance is less than 5%, we can say that this probability is small enough to say that, or at least let us conclude that, no, it was not due to pure chance, and that algebra students are actually strictly greater than, or strictly better than the calculus students. So let's move on to continuous random variables. So a random variable is continuous if and only if its cumulative distribution function is continuous. So that's our definition here. That means our variable can take any value along the real line, and then the probability of that continuous random variable being any specific value should be 0, because there's an infinite continuum of values that it can take. So when we deal with continuous random variables, it makes sense to talk about the probability of that variable lying within an interval rather than taking a specific value. So if x is continuous random variable with a cumulative distribution function f, capital F, then the probability density function is defined by lowercase f is the derivative of capital F, and therefore, yes. So now, the probability density function. So this is the property of the probability density function, which models our continuous variables. So the function needs to be greater than or equal to 0 for all x. Also, the probability, the cumulative density function, distribution function, sorry, or the CDF, is the integral of our PDF from negative infinity to x. Additionally, if we integrate our PDF from negative infinity to infinity, that should be equal to 1. And the important part here is to find the probability of our random variable lying within some range, a to b. That is the integral from a to b of our probability density function. To find the expected value of a random continuous variable, wherever we saw a sum previously in a discrete case, that should just become an integral in the continuous case. So the expected value of x should be the integral from negative infinity to infinity of x. So that's another way of saying the integral over all possible x values. If we, again, previously we saw that if we applied a function to the random variable, then we apply a function within the integral. That's the same thing here. And also, we can calculate our variance using our standard formula. Variance of x equals e of x squared minus mu squared. So a question here. A continuous random variable x has a probability density function given by this here. So find the value of alpha. So to find the value of alpha, remember the properties of our probability density function. The first and most important property is that if we integrate our PDF from negative infinity to infinity, it should be equal to 1. So we can use that to find alpha. So actually integrating this expression, alpha 1 minus x squared dx, from 0 to 1, because our function is defined to be 0 for all values that are not between 0 and 1, we get that integral is equal to 2/3 alpha, so then alpha should be equal to 3 over 2. Now the second part is to find the expected value. So remember, our expected value is the integral of x, f of x, from negative infinity to infinity. Actually, doing this integral, performing the integral, we get 3 over 8. And to find the variance, we use our formula, e of x squared minus e of x whole squared, and where we found e of x in the previous part. So just actually performing that integral, we should get the variance is equal to 19 over 320. So an important idea when we're dealing with continuous variables is something called standardization. So if we have a random variable x and we transform that to become x minus mu on sigma, that is our new random variable z, and we can say that z is standardized because its expected value is always 0 and the variance is always equal to 1. And that comes in handy when we're talking about the normal distribution. So a continuous random variable with a probability density function defined by this equation here is normally distributed with a mean mu and a variance sigma squared. And if we're talking about the standard normal distribution, so in other words, when we apply the transformation x minus mu on sigma, it should have a mean of 0 and a standard deviation of 1, as we saw. To actually calculate normal probabilities, we see that this function is not integrable in terms of elementary functions. So what we do is use our normal standard normal table. So if we transform our random variable to be the standard variable z by taking x minus mu on sigma, what we can do is determine our probability values from a table or using Maple. So let's go ahead and apply that in a question here. So Mo's mobile phone company produces phones with an average lifetime of 4.2 years. So suppose that the lifetime is approximately normally distributed with a standard deviation of 1.3 years. Mo wishes to offer a warranty on his phones, but figures that it's only profitable to do so if he replaces fewer than 2% of the stock that he sells. So what warranty length should he offer. So now the question here is, what probability are we finding, or how do we find the warranty time t? So we know that the probability, so if we first define x to be some random variable that is the lifespan of the phone, we want the probability that the lifespan of the phone being less than some warranty time t is less than 2%. So in other words, the probability of a phone lasting less than the warranty time t is 2%. So that gives us the probability of x being less than or equal to t is less than 0.02. So first step, we need to standardize it by taking x minus mu on sigma. And now that probability becomes the probability of z being less than or equal to t minus 4.2 on 1.3. Now we wish to find the value of t minus 4.2 on 1.3 such that the probability of z being less than this value is less than 2%. So looking at our table of standard normal probabilities, the probability of z being less than negative 2.05 is roughly 2%. So substituting that in gives us a value of t to be 1.535 years. And hence the warranty length should be approximately 1.535 years. In the case that we have large binomial distributions with a lot of repeated trials, then it's difficult to calculate the probabilities using our distribution for the binomial case. So what we realize is that the normal distribution approximates the binomial distribution quite well for large values of n. But the only issue here is that we're going from a discrete case to a continuous one. So we need to apply something called a continuity correction. And that just comes from the fact that the probability of x equaling some random value, so let's say 10, for a continuous case is always 0 because point probabilities are 0. But if I'm talking about the discrete case, it makes perfect sense to be asking what's the probability that x equals 10. So to actually, when we go from the discrete to the continuous case, when we apply this approximation, what we need to do is apply the continuity correction. So what that means is adding plus minus 0.5 on either side. And a list of general rules of thumb when it comes to applying the continuity correction is found in this table. And you can get these slides later on when we upload them to the website if you want to see this table in your own time. So now let's apply this in a question here. So the Australian No Hopers Party claims that 6% of voters support them. In a survey, 500 people are asked about their voting intentions. So assume that the party's claim is true. So 6% of voters support them. And let x be the random variable, giving the number of voters in a survey who support them. Then x will be modeled by a binomial distribution. Then find the mean and variance. So in this case, the probability is 6%. And we're saying success here is that someone supports them. So in this case, the probability, or at least the expected value of x should just be NP. And remember, we had 300 people. So then therefore, 500 people. Therefore, we should just get 30 for the mean and 28.2 for the variance, just applying our known formulas. So now the next part of the question is, when the survey results are published, it is found that 22% of the 500 people supported the party. Use the normal approximation to the binomial to estimate the probability that x is at most 22. So in other words, we want to find the probability of x being less than or equal to 22. So using the normal approximation to the binomial distribution, x is approximately normally distributed with a mean of 30 and a variance of 28.2, right? So then to find the probability that x is less than or equal to 22, the first step we do is, first apply the continuity correction, right? And that becomes the probability of x being less than or equal to 22.5. Then remember that we can't actually determine this because we can't integrate the PDF. So we standardize it by taking x minus mu on sigma. And now that's the same as the probability of z being less than or equal to negative 1.41 approximately. And then I apply a few transformations using the symmetric properties of the normal distribution just to transform into a value that is actually in our Z table. So you can see that the probability that Z being less than or equal to negative 1.41 corresponds to the area here if this is negative 1.41, right? Because the normal distribution is symmetrical, this area is equivalent to the area on the right side of the curve. So in other words, that's the same as the probability of Z being greater than 1.41. And this probability is the area of the curve greater than 1.41. And that area is the same as the area of the entire curve, subtract the area less than 1.41. Because we know the area of the entire curve should be 1, this just comes down to 1 minus the probability of Z being less than or equal to 1.41. And using our our standard normal table, we should get a probability here of 0.0793. So moving on to the next part, this is the exponential distribution. This is only relevant to MATH1231. So in this case, right, previously we discovered, I guess, that the normal distribution models the binomial distribution for large N. The exponential distribution is a continuous model for the geometric distribution in large N, analogous to the previous binomial and normal case. So we say that a random variable t with probability density function given by this piecewise function is exponentially distributed with parameter lambda. So the expected value of t is 1 on lambda, and the variance of t is 1 on lambda squared for this distribution. So a question here is a company finds that on average 0.05 of its customers return a particular product as faulty within the 6-year warranty period. Assuming that the number of returned products follows an exponential distribution, find to 3 decimal places the probability that the first claim occurs within twice the warranty period and between 6 and 9 years. So we're given a probability p here, but remember when we're dealing with an exponential distribution, that is in terms of some parameter lambda, right? So if t is the number of warranty periods before the first claim, then t is exponentially distributed with lambda. But we're not given a lambda value, we're given a value for p. But we use the fact that in the exponential distribution, there's a relationship between p and lambda. And what this comes from is looking at the relationship between the exponential distribution and the geometric distribution. I won't derive that now, but it's in the course notes if you want to look at that. But actually substituting our value of p is equal to 0.05, we should get a value of lambda approximately 0.05129. So then t is exponentially distributed with lambda equals that value. Now all we want to find is the probability that t, right, the number of warranty periods, and importantly note in this question, warranty period is not the same as a year because we say that one warranty period is 6 years, so keep that in mind. So we want to find that t is less than or equal to 2 warranty periods. And actually doing that is the same as taking an integral over the probability density function from 0 to 2. And actually calculating that using our value of lambda, we should get approximately 0.09. So that is the probability that the first claim occurs within twice the warranty period. Now, the second part to this question was to find the probability that the first claim is within 6 and 9 years. So we know that because one warranty period is 6 years, 9 years corresponds to 1.5 warranty periods. So all we're looking for here is the probability that t is between 1 and 1.5. And that comes to the integral of the probability density function from 1 to 1.5, giving us 0.024. So that's the probability that the first claim is within 6 and 9 years. So that's it for the course. But we have one more resource that we made at MathSoc. That is a revision sheet for MATH1231 and MATH1231. So if you scan the QR code, you can get access to the revision sheet. So it pretty much has all the important theorems, everything you need to know, the definitions of all the stuff we went through, like kernel, null space. If you ever forget, you can just look at the revision sheet. So it's just a set of succinct notes that sort of summarizes the whole course. And we also have sheets available for Math 1081 if you're taking that. I'm assuming you've already taken Math 1A, so that's not too relevant. But maybe you want to give it to your friends. So I'll just leave that up here for a second. It's also available just on the website, so go to UNSW MathSoc, Google that. And also, thanks to you for coming, everyone. We have a QR code here, and it's a feedback form. If you have any feedback for the revision seminars, if you came yesterday as well, or if you watched the live stream or video recording for yesterday, then let us know if there's anything we can do to improve our revision seminars for next term and over the next few years. And also, big thanks to Ronald for the first part.
Okay.
Yeah, we're done.
I think that's all. Yeah.
Yeah, that's it.
Thanks for coming. We're going to end the stream now.